Welcome back. In this video, you'll learn about Taylor series and Maclaurin series. Let's get to it. Alright, so far we have seen how to represent functions as power series when the function, its derivative, or its integral were in a form similar to the sum of a geometric series. But that is not the only way that we can represent functions as power series. And so this is where the concept of Taylor series and Maclaurin series are going to come into play. All right, and so let's get started by taking a look at the general form of a power series, right? Remember that we said that a function f of x is formed by a power series of this form, where we have the sum from n equals 0 to infinity of some sequence a sub n times x minus c to the power of n. And of course, that value of c determines where the power series is centered. All right, so if we were to write out the terms of this general form of a power series, this is what we would find for f of x. F of x would be equal to the first term when n equals 0, where we'd have a sub 0 times x minus c to the power of 0, but anything to the power of 0 is just 1. So we would have a sub 0 times 1, so we just have a sub 0. Then we'll add that to the term when n equals 1, so we'll have a sub 1 times x minus c to the power of 1, but we don't really need to write that power of 1. And then we'll add that to the next term when n is equal to 2, so we'll have a sub 2 times x minus c squared, and then let's write out the term when n equals 3. We'll have a sub 3 times x minus c cubed, and then I'm going to skip ahead to our nth term, where we have a sub n times x minus c to the power of n, and then of course our series would continue on from there because it goes on for infinity, right? From n equals 0 to infinity. I just decided to highlight that nth term. All right, so hopefully this is nothing new right here. These are the terms of the general form of a power series, but what we're going to do now, in order to start talking about what Taylor series and Maclaurin series are, is start taking derivatives of this function, which is the general form of a power series, which means we're going to take the derivative of each of these terms. But we're going to do it multiple times. We're going to look at the first derivative, the second derivative, and the third derivative, and then what we're going to do is generalize the nth derivative of a power series. And that is going to help us formulate what Taylor series and Maclaurin series are. All right, and so let's start by looking at the first derivative, f prime of x. If we take the first derivative of this first term, a sub 0 is just a constant, right? It doesn't have x anywhere within it, and so the derivative of a sub 0, or the derivative of a constant, would just be 0, but we don't really need to write that, so I'm going to erase that. And now let's take the derivative of our next term, a sub 1 times x minus c. In this case, the derivative will be equal to a sub 1 times the derivative of x minus c, and the derivative of x is 1, and the derivative of minus c, which is a constant, will just be 0. And so a sub 1 times 1 would be the derivative of this term, which is just a sub 1. And then we're going to add that to the derivative of a sub 2 times x minus c squared. Now this time we would need to use the chain rule. We'll use the power rule for derivatives on this quantity of x minus c squared, and then we'll multiply by the derivative of the inside function. However, the derivative of x minus c, as we just said earlier, is equal to 1, so we don't need to worry about multiplying by that inside function. We can just keep using the power rule for derivatives on this quantity for all of our terms. All right, so if we multiply that exponent down, our derivative will be 2 times a sub 2, and that will be multiplied by the quantity of x minus c. All right. Then we'll add that to the derivative of this term, where n equals 3. And so we'll use the same derivative rules and have 3 times a sub 3 times x minus c squared, right? We multiply that exponent down and subtract 1 from that exponent, and now we have x minus c squared. All right, that's why we have x minus c to the first power here. We subtracted 1 from this exponent, so we just have an exponent of 1. All right, and then we're going to add up until the derivative of our nth term. So if we multiply this exponent down, we'll have n times a sub n times x minus c to the power of n minus 1, because we have to subtract 1 from that exponent. All right, and so then we could continue on with more terms from there. All right, so that's the first derivative of our function that is represented by a power series. Now let's take the second derivative. that's going to be f double prime of x. In this case, if we start taking the derivative of each of these terms, the derivative of a sub 1 will be 0 because a sub 1 is just a constant. So let's move on to our next term. The derivative of 2 times a sub 2 times x minus c. If you imagine we're using the power rule for derivatives here, this exponent of 1 would be multiplied down, and then you would subtract 1 from that exponent, and so this exponent would be 0, and x minus c to the power of 0 is 1. And so what we'd have is 2 times that exponent of 1 times a sub 2. And I'm going to leave it in this form of 2 times 1 times a sub 2 because what we're going to be doing here is looking for a pattern in how each of these derivatives is written out. And that's going to help us form the nth derivative of a power series, which is how we're going to find the form of a Taylor and Maclaurin series. Okay, so I'm not going to simplify too much. Let's just work on taking the derivative of each term of our first derivative. So we just did the first two terms here. And now let's move on to this term. We'll multiply this exponent down. So we'll have plus 3 times 2 times a sub 3 times x minus c to the first power, because if we subtract 1 from this exponent, we have x minus c to the first power. That's just the power rule for derivatives. Once again, we multiplied 2 down, and we subtract 1 from the exponent. Now, if we add up to our nth term, let's take the derivative of this term. We'll multiply this exponent down and subtract 1 from that exponent. And if we do that, we'll have n times n minus 1, and that's still multiplied by a sub n, and then we'll have x minus c to the power of n minus 2. And we'll continue to add terms from there. Right? If we subtract 1 from this exponent, n minus 1 becomes n minus 2. And so now, let's take the derivative one more time. Let's take a look at f triple prime, the third derivative of our power series, by taking the derivative of each of the terms from our second derivative. In this case, the derivative of 2 times 1 times a sub 2 is just going to be 0 because 2 times 1 times a sub 2 is just a constant. A sub 2 is a constant, and 1 and 2 are also constants. And so that term will become 0, but I'm not going to write that. So let's move on to our next term. We have 3 times 2 times a sub 3 times x minus c to the first power. We'd multiply that first power down, subtract 1 from that power, and so we'd have x minus c to the power of 0, which just becomes 1. So all we're left with is 3 times 2 times 1, that power we multiplied down, times a sub 3, and then we'll add up to our nth term. And so let's take the derivative of this term by multiplying this exponent down and subtracting 1 from it, and we'll have n times n minus 1 times n minus 2, that's the exponent that we multiplied down, and then we'll have a sub n times x minus c to the power of n minus 3, because we have to subtract 1 from that exponent, so n minus 2 becomes n minus 3, and we will add the rest of our terms from there. All right, and so now we have the first, second, and third derivatives of this function, which is represented by the general form of a power series. And what's interesting to note about the first, second, and third derivatives is that the first term, or the term that is a constant, involves the value of n that corresponds to that derivative, right? The first derivative has a constant term with a sub 1, the second derivative has a constant term with a sub 2, and the third derivative has a constant with a sub 3. Those are the constant terms for each of these respective power series that are derivatives of the original power series. And so if we're going to write out the nth derivative, and this is how we would write that notationally, right? Remember that a higher order derivative past the third derivative, we have f and then a superscript of parentheses around the number for that derivative. This represents the nth derivative of a function. The first term of this nth derivative is going to be a constant involving the value of n, right? If we kept taking derivatives until we got to the nth derivative, this term would be the first term of that derivative, and it would be a constant. We would have n minus n as the power of x minus c. Okay, and so we would have a bunch of constants times a sub n, and then x minus c to the power of n minus n. So let's write that out. The first term of the nth derivative would look like this. We would have n times n minus 1 times n minus 2, and then you would continue to multiply by values 1 less than n until you get to 3, and then you would multiply by 2, and then you would multiply by 1, which would then bring you to a sub n, right? And that's multiplied by x minus c to the power of n minus n, which of course would be 0, and x minus c would be raised to the power of 0, and so that whole thing would become 1. All right, and then you could continue to add more terms from there for that nth derivative. But the first term is this term right here. This is our constant term where we have a sub n. Okay, and the reason I keep pointing that out, the reason I keep drawing attention to that first term, which is a constant term, is because what that says about each of these derivatives, or just the nth derivative of a power series, is that the nth derivative will always exist at x equals c, right? If we evaluated the nth derivative at the value of c, it would exist and it would just be equal to that first term, which would be a constant. For example, if we look at the first derivative, if we were to plug c into this derivative, a sub 1 would be part of that value, and then we would have plus 2 times a sub 2 times x minus c. Well, x would be equal to c because we're plugging c into the derivative, so c minus c would be 0, and so this whole term would become 0 because we're multiplying by 0. Then this term would also become 0 because c minus c is 0, 0 squared is 0, 0 times a sub 3 and 3 would also be 0. And that would be true for the rest of the terms of that first derivative. So all of the terms except that first term would become 0, which means that f prime of c would be equal to a sub 1. Now if we look at the second derivative, if you plugged in c into this second derivative, this first term would stay, 2 times 1 times a sub 2 would stay. There's no x's there, so we can't plug c anywhere in that first term, but then the rest of these terms would become 0. 3 times 2 times a sub 3 times c minus c would be 0, so this whole thing is 0, and that would occur for the rest of the terms. And then of course the same thing would occur for the third derivative as well. This first term would stay put, 3 times 2 times 1 times a sub 3, and then the rest of the terms would become 0 because you'd have c minus c, which is 0, and 0 times anything is 0. All right, and so if we take a look at those constant terms, I'm going to circle them here, and that would also include this term right here. What do you notice about each of those terms? Well, the first term, we have 1 times a sub 1. Then for the second derivative, we have 2 times 1 times a sub 2. Then for the third derivative, we have 3 times 2 times 1 times a sub 3. And then for the nth derivative, we start with that value of n, subtract 1 from that value until we get to 3 times 2 times 1, and then a sub n, and of course this would just become 1, because x minus c to the power of 0 is 1. And so what's happening is we have that value of a sub n times these constant values that would result from the expression of n factorial, right? That's what this is right here. This is n factorial. You would have n, then you would multiply it by a value 1 less than n, then multiply it by a value 2 less than n, all the way until you get to 3, 2, and 1, and then you would multiply by a sub n. And so let me write that in here. We have n factorial times a sub n. This right here is what the nth derivative at c is equal to. The nth derivative of c is equal to n factorial times a sub n. And you can see that for these other three derivatives that we wrote out. F prime of x, when n equals 1, we would have 1 factorial times a sub 1, and 1 factorial is 1. For this second derivative, n would be equal to 2. So we would have 2 factorial, which is 2 times 1 times a sub 2. Then for the third derivative, where n would be equal to 3, we have 3 factorial, 3 times 2 times 1 times a sub 3. And so the nth derivative evaluated at c exists, and it will always be equal to n factorial times a sub n. And so if I clean up my work here, this is the conclusion that we were able to make by looking at the derivatives of a power series, that the nth derivative of that power series evaluated at c will always be equal to n factorial times a sub n. And so why is this important? Why do we care what the value of an nth derivative would be when x equals c? Well, watch what happens if we solve for a sub n. If we solve for a sub n, what we'll have to do is divide both sides by n factorial, and so we would have that a sub n is equal to the nth derivative evaluated at c divided by n factorial. And since a sub n is equal to that expression, we could replace a sub n in the general form of a power series with that expression, right? We could say that a power series, f of x, is equal to the sum from n equals 0 to infinity of a sub n, which we're going to replace with this expression. So we'll have the nth derivative evaluated at c divided by n factorial times x minus c to the power of n. And this function right here, or this series, is what we call a Taylor series. Specifically, it's a Taylor series centered at the value of c. All right, and so that is what a Taylor series is. This is what a Taylor series looks like that is centered at c. Okay, and so if I clean up my work here, let's write out the first couple terms of this Taylor series just so that you can see what they look like. The first term, when n equals 0, we'll have the 0th derivative of c. Now that doesn't really make sense, right? What is the 0th derivative of a value? Well, if n is equal to 1, this would be the first derivative. N equals 2, we would have the second derivative. So when n equals 0, well, that would just be the equivalent of the actual function itself. There is no such thing as a 0th derivative, so I'm going to stop saying that. Instead, what we would have here is just our function evaluated at c. All right, so when n equals 0, that nth derivative just becomes the function evaluated at c. And then that will be divided by 0 factorial. All right, and then don't forget to multiply by x minus c to the power of n, which is 0. Then we'll add that to our term when n equals 1. And so we would have the first derivative of c divided by 1 factorial, and that would be multiplied by x minus c to the first power. And then let's write one more term. We would have plus f double prime, that's when n equals 2. We have the second derivative, and that's evaluated at c divided by 2 factorial times x minus c to the power of 2, and we could add more terms from there. All right, and so if we simplify, 0 factorial is just 1, and x minus c to the power of 0 is 1, so this would be equal to f of c, and then we'd add that to f prime of c divided by 1 factorial, but 1 factorial is just 1, so we have f prime of c times x minus c to the first power, but we don't need to write that first power, and then we'll add that to f double prime of c divided by 2 factorial, which is just 2, because 2 factorial is 2 times 1, which is 2, and so we have the second derivative of c divided by 2 times x minus c squared, and so on. Okay, so those are what the first couple terms of the Taylor series centered at c would look like. And so now you have officially been introduced to the Taylor series. All right, but what about the Maclaurin series? What exactly is a Maclaurin series? Well, it's actually not too difficult. All a Maclaurin series is a Taylor series that is centered at 0. All right, a Maclaurin series is just a Taylor series where that value of c is equal to 0. And so here's what that would look like. If we rewrote our form of a Taylor series where c was equal to 0, we would have that a Maclaurin series would be f of x is equal to the sum from n equals 0 to infinity of the nth derivative of c, which is now 0, divided by n factorial, times x minus c, which is 0, to the power of n. But now x minus 0 is just x, so this would just be x to the power of n. All right, and so this right here is the form of a Maclaurin series. And I guess you could write that it's centered at 0, but that's a little bit redundant because a Maclaurin series is always a Taylor series centered at 0. All right, and so the first couple terms of a Maclaurin series would look like this. We would have our function evaluated at 0 divided by 0 factorial times x to the power of 0, but 0 factorial and x to the power of 0 are both 1, and so we'll just have f of 0. So f of 0 plus f prime of 0 divided by 1 factorial times x to the first power, but 1 factorial is just 1, and x to the power of 1 is just x. So I'll rewrite this to be f prime of 0 times x, and then the next term when n equals 2, we'll have the second derivative of 0, so f double prime of 0 divided by 2 factorial, but 2 factorial is just 2. 1 times 2 is 2, and that will be multiplied by x squared, and then we could add more terms from there. All right, and so that's what the first couple terms of a Maclaurin series would look like, which of course is just a Taylor series where c is equal to 0. All right, but now the actual value of these terms, what they would really look like for a specific function for both a Maclaurin series and a Taylor series is of course going to depend on the actual function, right? We would need to know what that function is to find f of 0, f prime of 0, f double prime of 0, and so on. Okay, and so just to summarize everything we went over, I always like to give you one of these summary cards if I can. What we have are two series. This series is the form of a Taylor series centered at x equals c, and this right here is the form of a Maclaurin series, which is just a Taylor series centered at 0. Okay, and so now that you know what a Taylor series and a Maclaurin series are, let's take a look at an example of representing a function as a Taylor series. Okay, so here's our first example. We want to find the Taylor series centered at c equals 0 for f of x is equal to e to the power of x. All right, and it's important to note here that since we are trying to find a Taylor series centered at c equals 0, another way to view this is that we are looking for a Maclaurin series to represent this function, because a Maclaurin series is a Taylor series centered at c equals 0. Okay, but putting that aside, here's the process we're going to go through in order to represent a function as a Taylor series, or in this case, a Maclaurin series. The process is not going to change based on Taylor series or Maclaurin series, so don't worry about that, but this is the process we're going to use. The first thing that you want to do is just write out the first couple derivatives of your function. All right, so remember, we were given that f of x is equal to e to the power of x, and then what you want to do is take the derivative of that function a couple times until you can start to maybe see a pattern in what is happening to that derivative. Okay, because our end goal is going to be to find a way to represent the nth derivative of this function so that we can use that nth derivative to write it as a Taylor series, or once again, as a Maclaurin series. Okay, because remember, we can represent a function as a Maclaurin series of this form, the sum from n equals 0 to infinity of the nth derivative evaluated at the value of c, which in this case is 0, and that will be divided by n factorial times x to the power of n. This is our form of a Maclaurin series. And so let's take the first couple derivatives of this function. And so f prime of x, the first derivative, is the derivative of e to the power of x, but the derivative of e to the power of x doesn't really change that function, so we're just going to have e to the power of x again, and so that's actually going to be our derivative every single time. So this is a fairly easy example, right? F double prime of x, the second derivative, will also be e to the power of x, and the third derivative will also be e to the power of x. All right, so it's a little unnecessary to write out all of these derivatives, but generally what you want to do for a function when you want to represent it as a Taylor series or Maclaurin series is write out at least the third derivative, maybe sometimes a fourth derivative, if it helps you identify a pattern. All right, but in this case, it's pretty easy to see that the nth derivative of x will just be equal to e to the power of x, right? All of the derivatives of this function, the first derivative, second derivative, and so on, are just going to be e to the power of x. And so now that we have identified what our nth derivative is, what you want to do next is evaluate each of your derivatives at the value of c where you want your Taylor series to be centered. In this case, c is equal to 0. So we would evaluate f of x at 0, and so we'd have f of 0 is equal to e to the power of 0, and anything to the power of 0 is equal to 1, and then we would plug in 0 for all of our derivatives as well. Okay, so we could go through and say f prime of 0 is equal to e to the power of 0, which is equal to 1, and do that for our other derivatives as well. But hopefully it's obvious that they're all going to be equal to 1, and so the nth derivative evaluated at 0 will be equal to 1 as well. All right, and so typically when you're working with other functions, you want to try to represent what this value would be in terms of n, but in this case there was no need for that because all of the values were the same. And so, since we know that the nth derivative evaluated at 0 is 1, we can now represent our function f of x, or e to the power of x, as a Maclaurin series, or a Taylor series centered at 0. All right, so what we have is that e to the power of x is equal to the sum from n equals 0 to infinity of 1 divided by n factorial times x to the power of n. right? We just replaced the nth derivative, evaluated at 0, with 1, because that's what we found that it would be equal to. And so if we simplify, we can just multiply x to the power of n into the numerator, and we would have that e to the power of x is equal to the sum from n equals 0 to infinity of x to the power of n divided by n factorial. All right, and so now we found a power series, or more specifically, a Maclaurin series that represents this function e to the power of x. All right, but we're not quite done yet. At this point, we need to determine the interval of convergence for our power series that we just found, okay? And that's actually nothing new at this point. You would just use the ratio test for this series to find the interval of convergence. Okay, but that's not really the focus of this lesson, so I'm just going to put the work up on the screen here, and you can see how we would use the ratio test to determine the interval of convergence, but hopefully you are used to using the ratio test by now for power series. I've gone through this process multiple times in previous lesson and examples videos, so if you're not quite sure on how to use the ratio test, be sure to check out those videos as well. And so if you want to look at this work a little bit further, feel free to pause the video and take a look at each step individually. But the most important takeaway from this work is that the interval of convergence for our series is negative infinity to infinity. So let's go back to our other work, and I'll make a note that this series converges for the interval from negative infinity to infinity. Okay, and so e to the power of x can be represented by this power series on this interval. And so I will box in that answer. We have the sum from n equals 0 to infinity of x to the power of n divided by n factorial on the interval from negative infinity to infinity. And that's equal to e to the power of x. And so let's take a look at another example. All right, so here's our next example. We want to find the Maclaurin series for f of x is equal to sine x. All right, now remember, when you want to find a Maclaurin series, that is the same as finding a Taylor series, but a Taylor series that is centered at 0. All right, so we're looking to represent this function, sine x, as the following power series. We want it in the form of a Maclaurin series, which is the sum from n equals 0 to infinity of the nth derivative evaluated at c, which will be 0, and that will be divided by n factorial times x to the power of n. All right, that's what we want f of x to be equal to. Okay, so the first step in getting to this form is to write out the first couple derivatives of our function. So if we do that, we know that f of x is equal to sine x. And so the first derivative, f prime of x, will be equal to cosine x, right? The derivative of sine is cosine. Then the second derivative, f double prime of x, will be equal to the derivative of cosine, which is negative sine x. Then f triple prime of x, or the third derivative, will be negative cosine x, because the derivative of sine is cosine. So negative sine becomes negative cosine. And then let's do another derivative. The fourth derivative will look like this. The derivative of negative cosine will be positive sine, because the derivative of cosine is negative sine, so that negative and this negative will cancel out, and so we'll have sine as our fourth derivative. All right, and now I'm going to stop there because now we've come full circle, right? We've gone from sine x being our original function to now having sine x as our fourth derivative. And so the derivatives from this point on, we just continue to cycle through these different functions. We would have cosine, then negative sine, negative cosine, then positive sine, and then the whole thing repeats again. Okay, and so in this case, finding the nth derivative is not as easy as it was in the previous example, right? When we had f of x is equal to e to the power of x, the derivative of e to the power of x is always e to the power of x forever. So it was really easy to find that nth derivative. But in this case, there's no way that we can represent the nth derivative of our function, right? There's no real pattern that we can follow other than the fact that the derivatives will cycle through these different functions. So in this case, we don't know what that nth derivative will be, and so let's just move on from that for now. Let's look at what happens when we evaluate each of these derivatives at our value of c, which is 0, since we want a Maclaurin series. C is equal to 0. All right, so f of 0 is equal to sine of 0, and sine of 0 is 0. Then we'll have f prime of 0, and so that would be cosine of 0, and cosine of 0 is 1. Then we have f double prime of 0, And so negative sine of 0 will still be 0 because sine of 0 is 0 and negative 1 times 0 is still 0. So we have 0. Then we'll have f triple prime of 0, which means that we would have negative cosine of 0, and cosine of 0 is 1 times negative 1 will be negative 1. So we have negative 1 for the third derivative evaluated at 0. And then for our fourth derivative, if we evaluate that at 0, we will have 0 because sine of 0 is 0. All right, and so once again, there's no way for us to determine what the nth derivative of 0 will be equal to. There is no clear pattern that we can represent with n for the values of our derivatives evaluated at 0. The only thing that we know is that they're going to cycle between these values of 0, 1, 0, negative 1, and 0. After this 0, we would be back to 1, then 0, then negative 1, then 0, and then we would repeat over and over and over again. Okay, and so there's no clear way to represent the value of the nth derivative at 0, and so what we have to do in this case is just write out the first couple terms of the Maclaurin series using these values and see if we can find a pattern within those terms to then come up with a way to write it as a power series. All right, so if I clean up my work here, let's write out what the first couple terms of this Maclaurin series would look like. So first up, we would have f of 0, right? We would have the 0th derivative of 0, but the 0th derivative would just be the original function. So we have f of 0 divided by 0 factorial, which is just 1, times x to the power of 0, which is 1. So we just have f of 0 when n equals 0. Then our next term, when n equals 1, we'll have f prime of 0 times x, right? We would have the first derivative of 0, f prime of 0, and that would be divided by 1 factorial, which is just equal to 1. So we still just have f prime of 0, and then we're multiplying by x to the power of 1, which is x to the first power. All right, then we'll add this to when n equals 2. So we'll have f double prime of 0, which is the second derivative, and that will be divided by 2 factorial times x squared. And then when n equals 3, we'll have f triple prime of 0 divided by 3 factorial times x cubed. And then let's do our fourth derivative, since we know what that value is when c equals 0. So we'll add that to the fourth derivative, evaluated at 0, divided by 4 factorial times x to the fourth power. And of course there would be more terms from there, but I'm not going to worry about writing those for now. Okay, and so let's plug in the values that we know for these terms that would represent the Maclaurin series for our function. We know that f of 0 is 0, so we don't even need to write that first term, but I'm going to write it in here anyway for now. All right, so this is equal to 0 plus f prime of 0 times x. F prime of 0 is 1, so we have 1 times x, and we'll add that to f double prime of 0, which is 0, and so we have 0 divided by 2 factorial. But 0 divided by anything is 0, and 0 times x squared will be 0, and so that whole term just becomes 0. All right, and then if we move on to our next term, we have f triple prime of 0, which is negative 1. So we'll have negative 1 divided by 3 factorial. So I'll write that, negative 1 divided by 3 factorial times x cubed. And then our next term, we have the fourth derivative evaluated at 0, which we know is 0. And so just like with our term f double prime, this whole term is just going to become 0. Since the fourth derivative of 0 is equal to 0, we have 0 divided by 4 factorial, which is 0, times x to the fourth, which is still 0. So we're adding 0, which means that so far we only really have 2 terms to work with here. So I'm going to go ahead and write one more term here, because remember that the value of our derivatives at 0 is just going to cycle through. So the fifth derivative of 0 would be equal to 1, right? The fifth derivative of our function would be cosine of x because the fourth derivative was sine. So the fifth derivative would be cosine, and cosine of 0 is 1. And so that would lead us to our next term, which would be the value of the fifth derivative at 0 divided by 5 factorial times x to the power of 5. And like I just said, the value of the fifth derivative at 0 is 1, so we have 1 divided by 5 factorial times x to the fifth power. So I'm just going to rewrite this. We'll have 1 divided by 5 factorial times x to the fifth power. Okay, and of course there would be more terms after that, but I'm not going to write any more. So if we simplify, this would be equal to x plus negative 1 divided by 3 factorial times x cubed. But I'm going to bring that negative out front. Let's just subtract this whole term. So instead of having plus negative 1, we'll have minus 1 divided by 3 factorial. And then let's add our other term of 1 divided by 5 factorial times x to the 5th power. Okay, and then we can multiply x cubed and x to the 5th power into the numerators if we wanted to. So I'm going to do that. We'll have x cubed in this numerator. So we'll have x cubed divided by 3 factorial. And then in this other term, we will have plus x to the 5th power divided by 5 factorial. Okay, and so these are the terms that we have. And so you can start to see the pattern that is occurring with each of these terms. Right, we start with a positive term where we have x to the 1st power divided by 1 factorial. Then we have a negative term of x cubed divided by 3 factorial. Then we have a positive term of x to the 5th power divided by 5 factorial. And so following this pattern, we could conclude that the next term would be negative x to the 7th power divided by 7 factorial. Right, our powers of x are the odd numbers starting at 1, and then we're dividing by that value of that power factorial. And every other term is going to alternate in sign, because if you look at the value of our derivatives, we only get a term that isn't 0 when the derivative is 1 or negative 1. And so the sign of our terms is going to alternate between being positive and negative as we cycle through those derivatives. All right, and so we could continue to add more terms from there, but how could we express these terms as a power series? Or more specifically, in this case, a Maclaurin series. What type of pattern do we have in our terms here that we can represent as a series? Well, if I clean up my work, like I mentioned earlier, our powers of x are all odd powers, and they keep increasing by 2, right? We start with a power of 1, then a power of 3, then 5, then 7. Next would be 9 and 11, and so on. And then we are dividing by the value of that power factorial. And then our terms are also alternating in sign. So what we can do is say that these terms will be equal to the sum from n equals 0 to infinity of negative 1 to the power of n, right? We could at least say that because we know that our terms are alternating in sign. So we could put negative 1 to the power of n and not n plus 1 because our first term is positive. And so negative 1 to the power of 0 would be 1. So our first term would be positive. So that's good. And then also in the numerator, we have x to the power of a power that is odd. All right. And the way we can represent that is with 2n plus 1. When your series starts at n equals 0, this expression with n will ensure that that power will always be the next odd number for every term. Right? When n equals 0, 2 times 0 is 0 plus 1 will give us a power of 1. When n equals 1, we'll have 2 times 1 plus 1, which would be 3. When n equals 2, we have 2 times 2, which is 4, plus 1, which is 5. And so for every value of n, this power will continually become the next odd number. All right, and so that will be the power of x. And then we will divide that by that same power, but factorial. So we'll have 2n plus 1, which represents the odd numbers, and then we'll have factorial. All right, and so this power series here is the Maclaurin series, which is a Taylor series centered at 0 that represents these terms, which represents this function sine of x. All right, and so that's how you can represent a function like sine as a Maclaurin series, even though there wasn't a clear pattern with the value of our derivatives at the value of c. Okay, but now just like our previous example, with our function of e to the power of x, we do need to know the interval of convergence for this series as well. And so we would need to use the ratio test here. And so once again, I'm not going to go through that work from scratch. I'm just going to put the work up on the screen here for you because this video is not focused on the ratio test and finding the interval of convergence. I have another lesson on that topic that if you're not familiar with this process, you can watch that to get familiar with it. But here's how the ratio test would look for this example. And so if you want to pause the video and look over this work, feel free to do so. But once again, just like with our previous example, the most important takeaway from this work is that the interval of convergence is from negative infinity to infinity. So if we go back to our example, this power series represents sine of x for all the values from negative infinity to infinity. All right, and so that is the final answer for this example. We found a power series, or more specifically, a Maclaurin series that represents our function. All right, and so now that we have a power series, or a Maclaurin series that represents sine of x, and we know that the derivative of sine is cosine, we could also find a power series or a Maclaurin series to represent cosine. And the way we're going to do that is by simply taking the derivative of the power series that represents sine of x. Now you could go through term by term and see how the derivative would affect each term individually, but if you remember from a previous lesson, we can take derivatives of power series by just using the power rule for derivatives on the part of the power series that involves x. Right, so if we differentiate both sides here, the derivative of sine is cosine x, and so that will be equal to the derivative of this power series, which if we use the power rule for derivatives, we will have the sum from n equals 0 to infinity of negative 1 to the power of n times the derivative of x to the power of 2n plus 1. So what we'll do to use the power rule of derivatives is multiply this exponent down, so we'll have 2n plus 1, and then we'll multiply it by x and subtract 1 from that exponent. So we'll have x to the power of 2n plus 1 minus 1, but that 1 and that minus 1 will cancel each other out. So we just have x to the power of 2n, and this is all divided by 2n plus 1 factorial. Now we can actually simplify this a little bit. If we rewrite 2n plus 1 factorial by multiplying this value by a value 1 less than it factorial, right, we could say that 2n plus 1 factorial is equal to 2n plus 1 times 2n factorial, just like we can say that 4 factorial is equal to 4 times 3 factorial, because 3 factorial is 3 times 2 times 1, which would give you 4 factorial. And so you can always take the value of your factorial, multiply it by a value 1 less than that value, and then have the factorial there. So what we can do is have that cosine is equal to the sum from n equals 0 to infinity of negative 1 to the power of n times 2n plus 1 times x to the power of 2n divided by 2n plus 1 times 2n factorial. And now we have 2n plus 1 in the numerator and denominator, and so those will cancel out, which leaves us with the sum from n equals 0 to infinity of negative 1 to the power of n times x to the power of 2n divided by 2n factorial. And this right here is the Maclaurin series that would represent cosine of x. All right, and this would be defined for the same values of x. The interval of convergence for cosine would also be negative infinity to infinity. Whenever you take the derivative of a power series, sometimes you will lose or gain an endpoint, but in this case the endpoints are negative infinity and infinity, which can never be included, and so the interval of convergence will just be the same. So we now know that cosine x is equal to this Maclaurin series, which is defined for values of x from negative infinity to positive infinity. All right, so that's how you can find the Maclaurin series to represent cosine of x by using the Maclaurin series for sine of x. And these two Maclaurin series are actually two of a list of common Maclaurin series that are helpful to know. And so here's the first part of our list. These are common Maclaurin series that you might want to be aware of because they can help you represent functions that are similar to these functions as Maclaurin series. And we'll look at one example of that in this video before we bring things to a close. But here you can see that we have sine of x and cosine of x and what their terms would look like that are then equal to their respective Maclaurin series that are convergent for values of x from negative infinity to infinity. All right, but then we have some other Maclaurin series that are helpful to know. Here we have e to the power of x, which is equal to this series right here, which we found in our example. And then up at the top here, we have our very basic geometric power series, right? 1 divided by 1 minus x is in the form of the sum of a geometric series. That's equal to this power series, which is also a Maclaurin series. And of course, that power series is convergent for values of x between negative 1 and 1, but not including those endpoints. And then at the bottom here, we have the natural log of 1 plus x, which can be represented by this power series, and that is convergent for values of x from negative 1 to positive 1, including positive 1, but not negative 1. All right, and so these are the 5 most common Maclaurin series that you want to be aware of, but there are 2 more that you might want to see. And so here they are. We have arcsine of x, or the inverse sine function, and arctangent of x, or the inverse tangent function. Now, arcsine of x is pretty ugly. These terms are pretty nasty, and so is this series, but it is helpful to know, so you might want to write this one down. And this series is convergent from -1 to 1, including both endpoints. And arctangent of x is equal to this series, which is a Maclaurin series as well, and it's also convergent from -1 to 1, including those endpoints. Okay, so those are just some common Maclaurin series that you might want to take a note of because they're going to be helpful in representing functions similar to the functions on this list as Maclaurin series. And so let's take a look at one example of what I mean before we end this lesson. All right, so here's our last example. We want to find the Maclaurin series for f of x is equal to x squared times sine of 3x. All right, and so the reason why this is an example where knowing your common Maclaurin series is helpful is because we already know how to represent the sine function as a Maclaurin series, right? And so this function is similar to sine of x, and so what we can do is manipulate the common Maclaurin series involving sine into a form that represents this function, right? We already know from our list of common Maclaurin series, as well as our example from earlier, that sine of x is equal to the sum from n equals 0 to infinity of -1 to the power of n times x to the power of 2n plus 1 divided by 2n plus 1 factorial. All right, and that Maclaurin series was convergent for the interval from -infinity to positive infinity. And so if this is the Maclaurin series for sine of x, what would be the Maclaurin series for sine of 3x? What would that be equal to, right? Because that is part of the function that we want to find a Maclaurin series for. We will worry about the x squared later. We're actually going to be able to multiply that in because a Maclaurin series already deals with x raised to some power, so we can combine those powers. But before we get to that, how can we use this Maclaurin series right here for sine to find a Maclaurin series for sine of 3x? Well, all we have to do is replace x in this Maclaurin series with 3x. That's all we have to do. And so sine of 3x will be equal to the sum from n equals 0 to infinity of -1 to the power of n, but then instead of having x to the power of 2n plus 1, we will have 3x to the power of 2n plus 1. We just replaced x with 3x, and then we can divide by 2n plus 1 factorial. Okay, and so now we have a Maclaurin series that represents sine of 3x. But now what we have to do to get x squared times sine of 3x is to multiply this Maclaurin series by x squared. All right, and so x squared times sine of 3x, that's the function we want to find a Maclaurin series for, will be equal to x squared times the sum from n equals 0 to infinity of -1 to the power of n times 3x to the power of 2n plus 1 divided by 2n plus 1 factorial. Now we can combine x squared with this x in the numerator, but first we need to take this power to both of these parts, right? We can't just combine these powers by adding them just yet because we have different bases of x and 3x. But if we take 3 to the power of 2n plus 1 and x to the power of 2n plus 1, then we will have like bases that we can then combine. All right, so 3x to the power of 2n plus 1, we can rewrite that to be the following. We could have 3 to the power of 2n plus 1 times x to the power of 2n plus 1. All right, and now we have x to the power of 2n plus 1, and we're multiplying this series by x squared, so we can multiply that into the numerator and combine those exponents by adding them. X squared times x to the power of 2n plus 1 will be x to the power of 2n plus 1 plus 2, which will be 2n plus 3. So we can erase that 1 and have 2n plus 3, and then erase this x squared out front. And now what we're left with is the Maclaurin series that represents x squared times sine of 3x. This Maclaurin series represents that function. And then the interval of convergence for this Maclaurin series will be the same as the interval of convergence for the original sine function. And so if you want to make a note of that, this is also convergent from -infinity to positive infinity. Okay, so you can include that in your answer as well. That is the interval of convergence for that Maclaurin series that represents this function. All right, so when you use one of your common Maclaurin series to represent a function as a Maclaurin series, if the interval of convergence for that common Maclaurin series is from -infinity to infinity, that interval of convergence will remain the same for that function that you are representing as a Maclaurin series. The only time when that interval of convergence might change is when the interval of convergence for the common Maclaurin series is from -1 to 1, including or excluding those endpoints. And so that would be for 1 divided by 1 minus x, the natural log of 1 plus x, the arcsine function, and the arctangent function. Okay, and I explained that in more detail with an example in my examples video for this topic, and so this was the last example for this lesson, and so if you want to go ahead and see more examples of finding Taylor series and Maclaurin series, whether that be from scratch like we did in our first couple examples, or if it's by using common Maclaurin series, feel free to check out that examples video that I'll have linked at the end of this video, as well as in the description below. Okay, so if you have any questions, feel free to leave those in the comments below, but if you don't have any questions, this is all I had for now, so I will see you next time.